All right, welcome for our next video here for Chem 161, where we start to look at some Chapter 2 content, touching on the atom and the subatomic particles that are known to be present. Okay, so let's sort of sketch out a little chart here to help us with our discussion. As you may have learned in other courses, the atom, of course, is composed of three main pieces, and so we term these subatomic particles because they lie within the atom. And so the first type here is the proton. Okay, we know the proton to be positively charged. Okay, we typically indicate this with a plus sign, and that plus sign is typically in a superscript position next to a lowercase p to indicate a proton when in our sketches or other work to deduce this. And the location for the proton is, of course, in the nucleus. Excellent. Perhaps you also know that we have neutrons as well. Okay. These structures are subatomic particles, of course, and they are known to be neutral. That is, they have no charge. So no symbol for charge is necessary there. To be fully explicit, one could indicate a 0 up in that same position on the symbol for a neutron. And in this case, we would use a lowercase n to indicate neutron for diagrams or other types of scripting or drawings. Okay, and of course the position of this neutron, this is also found in the nucleus. Good. And the last subatomic particle that you're likely familiar with is, of course, the electron. And the electrons are known to be negative in charge. And so we would indicate that charge with a minus sign. And so to indicate in drawings or other representations of the atom, we would use a lowercase e and position that negative sign as a superscript off to the right, similar to what we did with the proton symbol. Okay, now the electrons are not in the nucleus, and in a simple planetary model for the atom, we would show these as orbiting the nucleus for the position of the electrons. As we dive deeper into the alternative and more sophisticated models for the atoms, we'll see that the idea of orbiting electrons will not be present in more sophisticated models, and we'll instead see three-dimensional wave structures for an electron. Okay. So putting all these pieces into our simplest model for an atom, we know that there's something called a nucleus, so that's what I've drawn here. And this nucleus may have a certain number of protons, so using our symbols from earlier, we could show a P with a plus sign. That nucleus may have neutrons, so we would apply the lowercase n. We know those also are located in the nucleus. And we'll see that the number of protons is signature to the type of atom that is in question. And there's typically a range of neutrons available to help distinguish isotopes of the same atom type from one another. So we can have carbon 12 or carbon 13 or carbon 14, which are distinguished by the number of neutrons within the nucleus. And now we need to apply our electrons, and our electrons, as we said, orbit the nucleus in our planetary model. So at some sort of orbit situation around the nucleus in the planetary model again, we would position the electron and show that it occupies a different sort of position in the atom. Okay, and so between the nucleus and the electron, of course, is empty space, and this is our planetary model for the atom. Okay, so building off that idea, you can see that it might be important to develop some syntax and some quantification to understand the structure of an atom more carefully. So we'll introduce at this point what is called atomic mass. And atomic mass here is just the mass of an atom. And the atomic mass of an atom is the sum of the protons and the neutrons. Okay? So let's define this first of all. So atomic mass of an atom is the sum of the protons, P plus, and neutrons, N. And we'll leave it at that. At this point, you're likely thinking, what about the electrons? Well, the electrons are so light in relative mass to these two other subatomic particles. They are roughly an 18/40th, so almost a 2,000th of the mass of a proton. So the electron's weight is termed as being negligible, almost insignificant. And so when we determine the atomic mass for atoms, our job is to simply count number of protons and number of neutrons, and we're allowed to ignore the contribution due to the number of electrons in that atom. Okay, so with this idea, we therefore have a follow-up term for us, which is now the atomic mass unit, termed AMU for short. And 1 AMU is the mass of one proton. One proton. It's also equal to the mass of one neutron. Okay. Also related to this is the fact that 1 AMU is also equal to 1 Dalton, capital D, lowercase a. And you may see Daltons reported for atomic mass or even ultimate molecular weights. And you'll especially see the units of Daltons in the domain of biochemistry if you go on into the sciences or other classes. Okay, so with that, we're able to start to capture the sort of weight of a single atom and ultimately the weight of many, many atoms, contributing to ideas like molar mass, which we'll see later in our course. Some other syntax that we need to help us understand the overall count of protons, neutrons, and electrons in an atom comes from information from the nucleotide. Okay, so a nucleide the nuclide shorthand that we're going to use here comprises of a major symbol to indicate the element in question. So X here represents that element that is represented from shorthand from the periodic table. So we'll show an example here for what X is in a moment. We're going to see that we're going to position some information up into this area as well as information into this area. So we're at the left-hand side of that, and we're going superscript or subscript on this. And over here in this area here, we're going to put symbol A, capital A. And this is what we term the atomic mass. For the nuclide. Okay, so atomic mass is also called the mass number. In the other field down below, we're going to put the atomic number. Okay, you'll see that the atomic number is roughly the order number of the element from the periodic table. So the first element would be hydrogen, that would be atomic number 1. Thereafter we would have helium, that would be atomic number 2. And so this number is given letter Z. Okay. So on the atomic mass, as you can see, based on our definition for counting subatomic particles that have overall mass that's significant, you can see that the mass number here is going to equal, this mass number is equal to the sum of the contributions from the total number of protons and neutrons. So we're going to have the sum of number of protons and neutrons. So that symbol here is indicating sum of. Okay. The atomic number is also known to be equal to the number of protons. So for hydrogen with only 1 proton, the atomic number Z would be 1. For helium with 2 protons, the atomic number would be 2. So Z equals 2 for helium. Okay. Some other details that we'll just make sure are driven home nicely here are element symbols. So be very cautious in how you put information here for X. Thinking about examples like that we've discussed here, things like carbon would be capital C for that. Other elements that are related to that you need to be cautious here about are things like cobalt, which also starts with a capital C, but we deliberately put a lowercase c to indicate cobalt and to distinguish that atom from carbon. Okay, so be very careful with your upper and lower case here as you position information at position X in the nuclide script. This could also be further distinguished from another example that we wouldn't put here. So I'm going to kind of put it in parentheses, and you want to not apply things like CO, both in the capitals, because this would indicate a molecular compound called carbon monoxide. And this is a different syntax for molecular compounds. Okay, so again, emphasizing the need to be very careful with how you put information in this scripting for the type of nuclide that we have. Okay. Good. So let's look at a couple of examples here before we end this video. So we'll look at carbon again. So we'll look at carbon 12. So notice that I've written out the name here and I've put the atomic mass number as a -12 here, and that's a correct way to list a specific isotope for carbon. That would be different from carbon 13, as you'll see. So if you turn to the periodic table, you would see that carbon is identified by atomic number Z equal to 6. Okay, so we know that Z equals 6 for carbon. We also know that the atomic mass number is 12, as we indicated above. So if that is 12, that we have a little equation here that there has to be 6 protons plus an unknown to sum up to the 12. So what we learn here is that the number of neutrons must be 6. Okay, so that's how the atomic mass or the mass number helps us understand the overall nuclear count of protons and neutrons. Okay, so applying our nuclide scripture to this, we can see that we're going to need to use capital C, not any additional information. We want to apply the mass number, 12, to the superscript left-hand position. And we want to apply the atomic number, which is the number of protons, as the subscript to the left position. Because we are talking about a neutral carbon-12, there's no need to put additional information as a superscript to the right, which is where we would indicate any imbalance between the number of electrons and protons in the atom. So for this overall electroneutral carbon-12 isotope, because we see nothing in that superscript right-hand position, we know that there is a perfect balance between the number of electrons and the number of protons, which means there are 6 electrons in this structure. So when we script all that, what have we learned? We've learned that the atomic number, of course, is equal to 6. This means that there are 6 protons in the nucleus. Because there's no overall charge, we also therefore know that there are 6 electrons to make the overall structure neutral in charge. So 6 times the positive 1 would be 6 plus without any electrons, and we neutralize all that with the 6 single charged electrons that are also present. We end up overall charge 0 there. And we know that the mass here, given from the mass number, is equal to 12 from the Z value, and that of course was 6 AMU from the 6 protons plus 6 AMU from the 6 neutrons to give the 12 that we have as the A value in this superscript left-hand position of our nuclide information. Okay, so we've said a few things here. Let's not forget that when we use the word atoms, that we are indicating overall neutrality. So that is balance, or a perfect balance between the number of protons and number of electrons. And when we look at ions later in the course, so I'll just sort of tuck that in here, you can see that we're going to have an imbalance. So these are going to be, the ions are going to be charged atoms, and this is going to come from the fact that the number of protons will not, so put a cross through my equal sign, will not equal the number of electrons in that case. And we saw the term isotopes as well. And isotopes would be different and distinguished, and I'll tuck in another example here for carbon 13, just indicate that here, and this would be different and indicated to be different here by knowing that the carbon still has to have 6 for the atomic number, Z, but it's going to have a different number of neutrons. So to give an A value that's larger, that is 13, we're going to need that information reflected here. Okay, so notice that these two are not equivalent, and one is indicating carbon 13, and one is indicating carbon 12. Okay, hopefully that has provided you with initial foundation here on some atomic structure and some of the atomic particles that are present and how we apply them in our planetary model for an atom, and how we can develop some scripture for the overall count of protons and neutrons, and ultimately the electron count by indication of the overall charge level. And we have a way to quantify mass here of an atom structure with the atomic